All right, well, thank you. You've heard a lot about Oklahoma. I'm going to try and give you a perspective about what it's like to be a seismologist in Oklahoma at this point in time. So I deliberately designed my talk to have time at the end for questions, so hopefully I get that right. I'm just going to sort of give you an idea of the current work we got going, new work that's going on, and sort of how things have developed in Oklahoma as I've been there for just these 5 years. So you've heard about this rate increase starting in 2009. It was just about the same time I walked in the door at the Geological survey. So I want to start off with my acknowledgement so I don't forget to do that. So I mentioned this new work we got going on. It's a RIPC grant, and we got cost shares from the Secretary of Energy, the Corporation Commission, and the OU Mewborn College of Earth and Energy to enhance our seismic monitoring capabilities, which are already quite good for a state in the central United States, but they're improving all the time. And then, of course, our industry contributors to RIPC, our industry contributors to our fault database that we'll hear more about, including the Oklahoma Independent Petroleum Association. And then the USGS has been incredibly helpful in providing additional instrumentation to help get a better understanding of the exact details of the earthquakes that are occurring. So at present we have well over 500 first motion focal mechanisms in our database, and half of those probably would not have been possible without the additional instrumentation provided by the USGS in key areas. So it's surprising to me, but still at this point in Oklahoma, I have to convince people that this rate change is real and significant. There are many people that say, well, your increase in earthquakes corresponds perfectly with the number of seismic stations operating in the state of Oklahoma. So you can see that this slide is a little bit dated. It was generated on October 20th of this year. But I like to point to the number of magnitude 4 or greater earthquakes. This is a yearly rate for number of magnitude 4 or greater earthquakes. We have a record of such earthquakes going back to 1882. So if we look at the rate of magnitude 4 or greater earthquakes from 1882 to 2008, we average about 1 every 10 years. And then in 2009, things began to pick up a little bit, and we averaged about 3 magnitude 4 or greater earthquakes each year. And you can see the numbers for 2014, and these are all probably pretty comparable magnitudes. Of course, when you're comparing magnitude scales over different time periods and measured in different ways, they can vary a little bit. So the number of 24 might be a little fuzzy, but either way, we're looking at a very distinct rate, as Andrea showed, from what we've seen in the past. And a magnitude 4 is large enough that it's felt throughout. If it occurs, say, in central Oklahoma, it's felt throughout primarily most of Oklahoma. If it occurs in northern Oklahoma, it's felt well into Kansas and down into central Oklahoma. These are felt over very broad areas of the central and eastern U.S. And so not a whole lot of these probably went uncaptured within the historical catalog. We probably have a fairly good accounting for all magnitude 4 earthquakes within the state of Oklahoma, give or take 1 or 2, but 1 or 2 or even 10 or 20 earthquakes in the period from 1882 to 2008 is not going to get us to what we're seeing still this year in 2014. And of course the magnitude 3 earthquakes show a similar story. We're fortunate enough to hire another seismologist. We started searching last year. Our new seismologist started, and of course we had another order of magnitude increase in the number of earthquakes. So there is actually just as good a correlation to the number of earthquakes in Oklahoma to the number of seismologists working within the Oklahoma Geological Survey as there are seismic stations. So one of the things we're looking at as a way to convince say management and others that this rate increase is real and something that we need to be concerned about is just calculating some simple probabilities just based on the Gutenberg Richter scale. So we're going to use the past 4 years of earthquakes or 1 year of earthquakes, whatever duration we choose. We're going to look back and use our A and B values then to look at the likelihood of at least 1 magnitude, say 3, occurring over that time period. And so the way we really sort of convince people that, hey, things are really exciting here is when we look at the probability of a magnitude 4, and I'm not sure when this was created, over a 6-month period, we're almost at 100%. And considering we're having one, or at least one, every 6 months of about 98%, and we're having a magnitude 4 roughly every 2 to 3 weeks. So, you know, these so far seem to be holding up pretty well. We haven't looked at using these in sort of an operational earthquake forecasting scheme, but we're going to begin to do that just to give perhaps the public an idea of what is the probability of, say, an intensity 7 earthquake within the area in which they're concerned with, their county or the areas in which they live. So this isn't a prediction. We can't predict earthquakes, but it's a forecast. And it's a great way to express that, yes, things have dramatically changed. We can compare the probabilities between just the 1 year and the 6 months, and they are quite dramatic. And it's a way to watch how things change if we then zoom in on different areas within the state as well. And of course, there was a question about, well, how soon before you can tell when things have changed? Well, my analysts have a pretty good feeling when seismicity within an area has changed significantly. We are quite busy just keeping our catalog up to date. Unfortunately, our catalog has suffered a little. So this is showing our A and B values from time starting in 2010. We're using a 6-month averaging window. And just to keep the axes the same here, we're just dividing our A values by 4 here. And you can see the effect of the magnitude 5.7 Prague earthquake in November of 2011 on this plot. But the real point is that things began to really increase, as well as our B values, and then as activity picked up in places outside of the Jones earthquake swarm, our B values began to drop in the state. And then with the large earthquakes, so the Prague earthquake, of course, our B value dropped much more. But then our A and B values sort of remained steady through most of 2012 and 2013. At the end of 2013, though, things began to change, and so we're seeing a whole lot more earthquakes and a much greater rate. But one of the things to point out here is our magnitude of completeness prior to this point right here was about a magnitude 1.9. At this point, we're at in the OGS catalog, we're complete now to about a magnitude 2.3. And that's simply because we can't keep up with all the small earthquakes. Something has to give. We have hired another analyst this year, but we probably need 2 more to get back down to our magnitude of completeness of about 1.9 to 1.8. We automatically locate earthquakes much smaller than that. But we don't put anything in our catalog that hasn't been reviewed so that it's a quality data source for researchers. We certainly are doing our best to keep that magnitude of completeness where it's at, but our threshold that we shoot for now is to make sure we're complete to that 2.5 magnitude threshold. And here's just the probabilities of these different size magnitudes, again, based on that same simple Gutenberg-Richter relationship through time. And you can see that we're now at about a 20% probability in a 6-month period of having a magnitude 5 or greater earthquake. So those are pretty good odds. We've been spending a fair amount of time going out into the public and educating the public about how to prepare for earthquake hazards. And of course, we started that, we were doing that even before the earthquake rate changes. So this isn't too different from what Andrea showed. So the greatest amount of earthquakes, or the greatest rate change, has occurred in this area highlighted by blue here. Of course, we have seen that there are other areas where the earthquake rates have increased within Oklahoma. We'll see that again here in a minute. But this area actually captures a very significant amount of the large volume wastewater disposal wells, and I'll show you that in just a minute. But just to show you how the number of earthquakes break down by this region. So in Andrea's talk, you saw them broken down for just magnitude 3 or greater. I just wanted to show you just the sheer numbers of earthquakes we've been recording in Oklahoma. So within that blue region of greatest increase, which includes about 15% of the spatial extent of the state, we're seeing very significant portion, the vast majority of our earthquakes are occurring within that region of central and north central Oklahoma, and we still see a rate increase occurring throughout the rest of the state. One of the areas that you'll is down here where we have some indication, and here as well where we've had some indication of earthquakes triggered by hydraulic fracturing within this region, and there will be a poster Friday on one such sequence that I encourage you to go look at. So this is a slide prepared by Kyle Murray, who's the geohydrologist at the Oklahoma Geological Survey. And this is a summary through 2013. So what Kyle's spent a lot of time doing is going through the Corporation Commission database. And as with any database that has a multitude of data sources and is often entered by hand, there are errors and mistakes within the database. So he goes through well by well and sanitizes the data set. This is very time consuming. He still is not complete with 2013. There's something like a couple hundred wells he has yet to process. So there are more than 10,000 Class II injection wells operating within the state of Oklahoma and more than 4,000 disposal wells. But as you can see, in 2013, the largest volume disposal wells shown in purple and blue are up here in the Mississippi Lime Play for the most part, and down here is also part of the Mississippi Lime Play, a little bit in the Hunton dewatering and the Arbuckle dewatering here in Oklahoma City. So we have a very large number of our greatest volume injection wells are within that area of greatest increase of earthquakes. So down on the bottom slide we have the injection zones, and so the light gray show the volumes from enhanced oil recovery, and the dark green shows the volumes by formation for saltwater disposal. And so by far the greatest unit of importance is the Arbuckle Formation. The Arbuckle Formation varies dramatically across the state, but it is a dolomitic limestone, highly fractured, cavernous, vuggy. Its matrix permeability and porosity are quite low, but it has all these secondary features within it. And then it overlies basement. There is often, in many places in Oklahoma, a unit that's referred to by a lot of different names, as sometimes the granite wash, and it's a rubbly, more porous zone that overlies basement and does not provide a permeability seal between this large disposal formation and the basement. So just to kind of flip back and forth so you can see where the earthquakes are occurring in relation to the disposal wells. Clearly there's some strong correlations and then areas where there isn't as good a correlation, and so those are interesting, and we continue to look at those. So now I'm going to talk about some new work we have going on with the RIPSI grant, and it's really designed to be a 4D geological or geophysical monitoring. So we're also doing then localized studies in specific areas where we can get more data or are of more curiosity. So we want to improve our model predictive capabilities. We want to be able to mitigate this, prevent these induced earthquakes from happening. And so we're going to maintain a suite of progressively updated 3D geologic models and 4D geophysical models and hydrologic models as well. And so we're going to improve our representation and perhaps understanding of preferential flow paths that may be quite important in Oklahoma, and then some of the geomechanical properties and fault characteristics in the subsurface. So it's a pretty daunting task. Sort of the first initial work was getting out and enhancing our seismic monitoring within the region. So this shows our Okra seismic network. This is a network of 12 stations augmenting what's already existing within central Oklahoma. And the gray stations here show permanent and temporary stations that throughout Oklahoma. In addition, we're going to be adding 9 new permanent stations. So the Okra stations are sort of meant to drop in to sort of augment the central Oklahoma area and the stations we already have and the stations we know we're going to be adding over the next couple months. So one of these stations is already available at the IRIS DMC. It's publicly available. It's KNG1. And so this station's located just on the edge of Logan and Kingfisher counties. There's a lot of seismicity within this area. And all the stations that the OGS operates are all available at IRIS, with the exception of the 11 other Okra sites. So then I mentioned the 3D geological and geophysical modeling. So this is just an initial effort to take a look at the top of the Hunton Formation. You heard the Hunton Formation described earlier, and then this bottom feature is the basement as we understand it today. So we can create surfaces and then volumes out of these surfaces with varying geological and geophysical properties. So a couple of interesting features here. We have the Nemaha Ridge or the Nemaha Fault, very significant down here in southern Oklahoma and also up into northern Oklahoma and the Kansas-Oklahoma border. Here we can see the Wilzetta Fault, on which the magnitude 5.7 2011 earthquake occurred. And then here on the edge of the Anadarko Basin is one of our most prominent faults, the Mears Fault, which last had an earthquake about 1,300 years ago of about a magnitude 7. Fortunately, it's the one area of the state that's fairly quiescent at the moment. Hope it stays that way. So we build these geological and geophysical interpretations at multiple scales. And so what scale is appropriate for me creating a 3D seismic wave model is very different than what's appropriate for hydrological modeling. And so I am very out of time. We're augmenting these with, oh, I still got the 3 minutes. I'm doing great. So we're also augmenting this with gravity measurements to help constrain our geologic models. We were hoping to maybe do 4D gravity to see if we can see any changes. Those changes from initial modeling look pretty small, and it could be a real challenge to capture that. So I mentioned the database that industry is providing to the state. So what's shown as the skinny blue lines here are the faults that I had compiled out of published literature from various sources, and there are many more sources out there that have yet to be compiled, and I have students working on that. But you can see then the red are faults provided by industry. So we went to industry and asked them to provide faults of significance, and we let them choose what significance was, and then we asked for some basic metadata. How were the faults defined? Were they defined by geologic tops from well logs? Were they defined by 3D seismic? And so you can see we've filled in areas where we had very little knowledge of faults within Oklahoma prior to this. And then we probably got some dumps of what I would not consider significant faults. Here, these little red splotches came straight out of a 3D interpretation out of a 3D seismic. So we are working on improving our understanding of the fault structures and the faults within Oklahoma. And the next talk will talk a lot about why that is so important to understand where these faults are and what the characteristics of these faults might be. So this has sort of been an evolving thing. Our interactions with the Corporation Commission, the Oklahoma Corporation Commission, is the regulator of UIC Class 2 wells within Oklahoma. This might be the only week that I haven't spoken to them this entire year. So this sort of shows an outline of sort of how the cooperation is now occurring, and really over here should be Mark's group as well, connecting into the optimally oriented faults, fault maps and earthquake locations, and other information or what we directly provide to the Corporation Commission on a daily basis through our online catalogs and that sort of thing. We're improving this fault database, and we continue to do these additional studies and work with collaborators as much as we have time to. So current mitigation steps, I'm at my time? All right. So I'll actually run through these real quick and then end here. So the Corporation Commission has implemented new rules regarding reporting within the deep injection wells in the Arbuckle. They're implementing a traffic light system, as you heard a little bit about, and they've created areas of interest around magnitude 4 and greater earthquakes, a 10-kilometer radius around these, where they go into a further review of injection activities, and new permits are checked against fault maps and background seismicity. Thank you.
Time for one question. See if you have any question. Repeat the question.
So with those 4 mitigation steps you have up there, when do you expect the radar seismicity to start rolling over?
That's a good, with the mitigation steps we have here, when do we expect the earthquake rates to start rolling over? That's a really good question. A lot of these have been implemented in the last year. And so there have been wells that have been taken offline, wells in review areas which were found to be exceeding their permits in one way or another, forced to either shut in or change the way they operate. So, you know, I think there's a lot more that we can do within the mitigation steps, but I am, of course, not the regulator. And so I hope that at some point I will have a chance to rest and get a handle on my research.